Hello, everyone, and welcome to Physics Lab. Today, I want to discuss one-dimensional motion. So in particular, we're going to look at constant velocity motion and constant accelerated motion of a cart on an air track. Now, again, this lab happens to be very similar for all of my three physics lab courses. So Physics 212, 207, and 206. So I'm just going to do one video lecture that kind of covers all three labs. The only difference is Physics 206 doesn't have to do the last part of it, but Physics 212 and 207, it's exactly the same lab. Okay, so let me begin by going over some theory, and then I'll discuss the lab itself. So first thing, linear motion is simply motion in a straight line. So that's what we mean by one-dimensional motion. Think of it as motion of a cart that's moving either to the right or to the left, right? Positive X or negative X direction on an air track. So it's linear motion, one-dimensional motion just along the air track. So for the first definition, actually, let me do most of this on an iPad so I can sort of describe it more carefully and explain each part of it. But the first definition is something called average velocity. All right, let me move over to the iPad. Okay, so in this example, let's assume I have a cart and it's initially at some position, I'll call it X sub I for initial, at some initial time, I'll call it T sub I. So the end of the car, the edge of the car is at that position at that particular time. Let's assume it's moving to the right. And at some later time, it's at some final position. So I'll label this as X final, so sub F, and then T sub F or T final, time final. So one thing that we may want to calculate is what is the average velocity of that car as it moves from the initial position to the final position. So by definition, the average velocity, and I'll define this as VAV, is equal to the final position, so X final, minus the initial position, X initial, divided by the final time minus the initial time. And then a more sort of succinct, efficient way of writing this is whenever we have a change like final minus initial, we can write that as delta. So you could write this as delta X over delta T. So this delta X, right, it means the change in position. But that has a special name that's called the displacement. So this is really the displacement. And of course, in the denominator, we have delta T, which is the change in time. So the average velocity is defined as the change in position or the displacement divided by the change in time of the object. In this case, it's the cart that's on the air track. All right, now a lot of what we're going to do in this in this lab is interpret graphs. So let me show you sort of what this looks like if we were to graph this information. Let's assume that we have our standard coordinate system. So X, Y, but we're going to assume that the X is time in seconds. And then on the Y-axis, I'm going to have position, which is in centimeters, let's say. And let's assume our graph is linear, right, just to start. So we'll assume that our position versus time graph looks like this. Right, so it's linear. So one thing we may want to do is we may want to calculate the slope of that line, right? It's linear, so let's calculate the slope. So to do that, I choose 2 points on the line. So let's say I choose this point right here. This maybe corresponds to time 1. And then this would be the corresponding position. I'll call it X1. And then let's say I choose this point right here. So this is say time 2, and this would be x2. Okay, but what is the slope? Well, the slope is going to be the rise over the run, right? In fact, let me just draw another parallel in here. This difference right here, that's the rise, but really that's going to be x2 minus x1, which we can write as delta x. And then the run, which is this distance, is really t2 minus t1, right? Which I can write as delta t. So this is t2 minus t1, but that another way around as delta t. And the slope, of course, is rise over run. So the slope in this case is rise divided by run. But in this example, that's going to be delta x over delta t. However, we just define delta x over delta t. What is delta x over delta t? It's the average velocity. So this is really just VF. So if you have a position versus time graph, right, and you have some curve, in this case, it happens to be the line. If you pick 2 points on that curve, and then you draw a line between those 2 points, and you calculate the slope of that line, that's going to be the average velocity over the time interval from t1 to t2. It's the average velocity over that time interval. Okay, now let's say that instead of the average velocity, we are more interested in what's called the instantaneous velocity. Like, what is the velocity right at this instant of t1? Like, let's say I want to know the instantaneous velocity right at time 1, right here, right at time 1. How do I find that? I know the average velocity from t1 to t2. How do I find the instantaneous velocity right at t1? What you do is you keep calculating the average velocity over smaller and smaller time intervals. So I'd leave the first point right there at t1, and I'd move the second point in. Like, let's say I move it here. Then I'd calculate the slope of that line. Then I move it in closer here, calculate the slope of that line. And when you get closer and closer and closer, right, to T1, you're moving T2 closer and closer and closer to T1. It turns out that the slope of that line is going to approximate the slope of a tangent line, which just touches the graph at that point at T1. So basically, ultimately, I'm going to get the slope of this line right here in blue. That's going to be the instantaneous velocity at that time T1 is the slope of that blue line. If I want to know it at some other point, let's say I want to know what is the velocity at this time right here. I'll call it T3. Well, I go to the curve, right? I want to know the instantaneous velocity at T3. I draw a tangent line to that curve right at that point, which is right there. And the slope of that tangent line is going to be the instantaneous velocity at that point. If I want to know it at some other point, let's say at this time right here, I go to the curve. I draw a tangent line, and the slope of that tangent line is the velocity at that point, the instantaneous velocity at that point. Now notice in this case, what's true about all these slopes at T1, T3, and at this other time out here? They're all the same, right? The slopes are exactly the same. So what that means is the instantaneous velocity is not changing. That means the velocity is constant. So if you have a position versus time, so position versus time graph, and it's linear, that represents constant velocity motion. So in this case, this is going to be constant velocity motion. Okay, because it's linear. All right, here's another case. Let's say I have a different graph, different position versus time graph. Let's say it looks like this. So again, this is going to be time in seconds on the x-axis and in position in centimeters on the y. Let's say this graph is parabolic, right? So it looks like a parabola like this. All right, Now, it depends on what you want to find out. Let's say I want to find the average velocity from this time, t1, to this time, t2. So I pick a point on the graph right at t1. That's going to correspond to some position. Let me call it x1. And same thing at t2. So I go up to the graph. Right, it's this point right here. It corresponds to this position, x2. And then I draw a line between those 2 points. So this is really called a secant line that connects those 2 points. So it looks like that. And then it turns out that the slope of that secant line, so the slope of that secant line, that would be delta, remember this is going to be delta x from here to here, over delta t, from there to there. So the slope of that secant line is going to be the average velocity over that time interval from t1 to t2. So this is just the slope of this line is the average velocity over the time interval from t1 to t2. I'll say time interval t2 minus t1. Right, it's the average velocity over that time interval. Now, just like before, we may not be so interested in the average velocity. We may want to find the instantaneous velocity at some point. So again, let's say I want to know what is the instantaneous velocity right at t1? What is the velocity at the instant? This is the average. The slope of this line is the average over that time period, right? Time interval. But what is the velocity right at the instant? Then again, just like before, what I do is I bring t2 in closer and closer to t1. So I make t2 say here, calculate the slope. This is still an average velocity, right? But now it's a smaller time interval. Then I bring it in closer, calculate that slope, bring it in closer. And eventually what you're going to find is that when t2 gets really, really, really close to t1, then the slope is going to be the slope of a tangent line that just touches the graph right at t1. And the slope of that tangent line is going to be the instantaneous velocity at t1. If I want to know at some other point, let's say I want to know at time t3 right here. I go to the graph and I draw a tangent line to the graph at t3. And the slope of that tangent line means it just touches the curve right at that point. That's going to be the instantaneous velocity at t3. If I want to know at this point out here, I go to the graph and I draw a tangent line right at that point. If I want to know it even earlier, go to the graph, draw a tangent line at that point. Now notice what's happening here. This slope, right, is getting steeper. The line is getting steeper, right, the tangent line. So the slope is increasing, which means the velocity in this case is increasing over time. So this is a case where the velocity of the object is increasing over time. Now, whenever you have a velocity that's changing, so if an object has a velocity that's changing somehow, then we have what's called an acceleration. So in this case, since the velocity is definitely changing, it's increasing over time, that means this object is accelerating. Now, the thing that's not so obvious, and you would need a little bit more math, including calculus, to really understand this, it turns out in this case that if this graph, this position versus time graph, is truly a parabola, then the acceleration would be constant. And that's the case that we're going to look at in lab, constant acceleration. But it's accelerating, happens to be constant. the thing that's important is that the velocity is changing. It's increasing over time. Okay, another definition. Let's say now that I have cart, let's say it's moving with some initial velocity. Let's say that velocity is, I'll call it Vx and then sub I for initial. And this is at some initial time, T initial. And then later, let's say it has a different velocity. So I'll say Vx final. And I'll just assume it's a larger velocity, right? Final at some time T final. So now that there is a change in velocity, right? This object is undergoing some change in velocity. We could define what's called the average acceleration. So usually write it as AAV. And that's equal, it's defined to be the final velocity minus the initial velocity. The x just means I'm moving in the x direction, right? One dimensionally along the air track, divided by the final time minus the initial time. Or more efficiently, I could write this as the average acceleration is the change in velocity in the x direction divided by the change in time. So whereas average velocity was change in position, right, delta x over change in time, delta t, average acceleration is like one step up, it's change in velocity over change in time. Okay, so one example would be this. Let's say I have, we'll look at a graph again. Let's say I have time on the x in seconds, and then velocity now on the y. Let's say it's in centimeters per second. And I'm going to assume it's linear again. Okay, so since it's linear, I might want to calculate the slope of this graph, right? So let me pick 2 points on the line. Let's say this corresponds to T1. This is going to correspond to my initial velocity, right, which is say V1. And let's say this point corresponds to T2. Then this would be my velocity at that time, which is, I'm going to call V2. And if I calculate the slope, I'm going to have the rise again here is going to be V2 minus V1, right, which I can write as delta V. And then the run is this distance right here, which is T2 minus T1, which I can write as delta T. So that means that the slope is delta V over delta T. But I just defined that. What is that? That's the average acceleration. So in this case, the slope represents the average acceleration. So if you have a velocity versus time graph, and it could be any function. In this case, it happens to be linear. If you pick 2 points on that graph, draw a line between them, which is really called a tangent line, and calculate the slope of that tangent line. And that's going to be the average acceleration of the object over that time interval. Now, just like before, we may not be so interested in an average acceleration. We might want to know the instantaneous acceleration at some time. So to do that, you basically calculate the average again, but you keep shrinking down that time interval. So if I want to know the instantaneous acceleration right at T1, well, I know the average acceleration from T1 to T2. Now I shrink down this time interval. I bring T2 closer and closer and closer to T1. So first I'd move it here, right? And then calculate that slope, which in this case is linear. So it happens to be the same, right? Then I move it in closer, calculate that slope. And you keep doing that until it gets closer and closer and closer. You basically, it's called taking the limit if you study calculus. And what you'll find is that the instantaneous acceleration at T1 is the slope of the tangent line that just touches the graph right at that point. So it's like the slope of this green line here. If I want to know at some other point, let's say at this point, call it T3, I go to the graph, I draw a tangent line, and it's the slope of that tangent line, and so on and so forth. So in this case, again, because it's linear, that slope is not changing. So what does that mean in terms of acceleration? It means the acceleration is constant, right? It's not changing. So if you have a velocity versus time graph that's linear, this represents constant accelerated motion. So this is a case where you have constant acceleration. Okay, now if you had a velocity versus time graph that's curved somehow, then the acceleration itself could be changing, right? But we're not going to look at that in lab. We're just going to stick with either constant velocity or in this case, constant accelerated motion. Now, one thing that we need, there's one formula that we need. We need to calculate the final velocity of the cart as it travels down the inclined air track. It's going to start at rest right before the flag intercepts the photo gate. And we want to know the final velocity of the car as the end of the flag passes through the photo gate. Now, this is not going to make more sense until you watch my little video. So I created a little video on how I collected this data. Please watch that video because it's too hard to describe in words like what's going to happen. But let me sort of just describe the formula, and you'll see when you watch that video, it'll make more sense. So we want to find the final velocity of that cart as the end of the flag passes through the photo gate. What we're going to do essentially is we're going to calculate average velocity two different ways. So because we know when a car is on an inclined air track, we have constant accelerated motion. It turns out that the average velocity is simply going to be the average of the initial and final velocities. Now, how do I take an average of two things? I add them up. I think I did. Let me make sure I use consistent notation. I think I did this all right. I said Vx and then initial, and then this would be Vx final. But then how do I average two things? I just divide by two, right? Add them up and divide by two. So the average velocity is simply the average of the initial and final velocities. This is only true if you have, this is true if you have constant acceleration. That's true. Now, another way I can calculate the average velocity is by definition. Remember, it's going to be delta x over delta t. This is all, that's always true. This one is true only under special circumstances if we have constant acceleration, but we're going to in this part of the lab. This one is always true. But these are both just two ways of writing average velocity, right? So they're equal. So these two equations should be equal. Now there's one last thing. If the cart starts at rest right before it triggers the photo gate, again, this will make more sense if you watch a little video. That means that Vx initial is going to be 0, right? So if this is 0, it's starting at rest. Now I can rearrange this formula. I can solve for the final velocity. And it turns out that the final velocity is going to be twice delta x over delta t. So basically the final velocity under these circumstances where we have constant acceleration and the cart is starting at rest, right, with 0 velocity, the final velocity is going to be twice the average velocity. Because remember, delta x over delta t is just the average velocity. So final velocity is twice the average velocity. But this is a very special case, right? It has to be those circumstances where you have constant acceleration and the cart is starting at 0. It's at rest when you release it. Okay, so that's a formula that we will need later to compute. Okay, so now I'm back at the handout. So let me just sort of do a quick review. So remember, the average velocity is defined as the change in position, right, which we can write delta x, which also is called the displacement, divided by the change in time, right? So delta x over delta c is defined as the average velocity. That's how it's defined. The instantaneous velocity is the rate at which a position changes with time at a particular instant in time. And graphically, remember, the instantaneous velocity is the slope of a tangent line that just touches the curve at one point, right? So like the slope of the line right there would be the velocity right at the instant. The slope here would be the velocity at this instant, and so on. But if we have a position versus time graph that's linear, see how the slope doesn't change, it's the same throughout. This is an example where we have constant velocity motion. If it's curved, right, then so the slope of this tangent line would be the instantaneous velocity right at that point right there, that slope. If I want to know the instantaneous velocity at this time, right, I go to the curve, I draw this tangent line, which is steeper now, right? That's going to be the instantaneous velocity at that point. In this case, the velocity is changing, right? In fact, it's increasing. It's getting greater and greater and greater. So if you have a position versus time graph that's curved, in this case it's parabolic, the velocity is changing. You have an acceleration. Okay, and we argued before, although this is not obvious, but mathematically, if this is truly a quadratic function, right, if it's a parabola, then it turns out we have constant accelerated motion. But the fact that the velocity is changing, we know we have an acceleration. All right, then we defined the average acceleration as being the final velocity minus the initial velocity over the final time minus the initial time, which we can write as the change in velocity over change in time. So whereas average velocity was change in position over change in time, this is like one step up. Average acceleration is change in velocity over change in time. And then graphically, so now instead of position versus time, I'm plotting velocity versus time. Notice that it's linear. I'm just going to start with a linear graph here. And in this case, if I choose some time, let's say 2 seconds, I go to the graph, I draw a tangent line to the graph at that point. That will be the instantaneous acceleration. If I want to know at 6, I go to line, draw a tangent line here, and the slope is the instantaneous acceleration. Since that slope is not changing, what does that say about the acceleration in this case? It's constant, right? So you can just remember, if you have a velocity versus time graph that's linear, it represents constant accelerated motion. You have constant acceleration. The velocity is certainly changing. It's increasing, right? Because we can see that this is velocity. As we move forward in time, the velocity is getting faster and faster and faster, but it's doing so at a constant rate, right? So we have constant acceleration. We're not really going to talk about this in lab, but this would be a case where I have velocity versus time. It's curved. So now the acceleration is actually changing. It's actually increasing in this case. Okay, and then the last thing we did was we derived this formula that we're going to need, right? We derived the final velocity of the cart if it starts at rest on an inclined air track right before it triggers the photo gate, and we want to find the speed of the cart as the end of the flag passes the photo gate. This is the formula we're going to use. It's twice delta x over delta t, or twice the average velocity. Okay, now that we've gone over the theoretical background, let's look at the lab experiment itself. So the first part of the experiment is going to be motion of that cart on the air track at constant speed or constant velocity. This is when the air track is flat, horizontal, and we're going to launch the cart at the same rate, the same speed every single time as it passes through. And again, you have to watch my other video on how I did this. So I show you how I actually collected the data. There's basically 5 different flag lengths that are placed on the top of the cart. And these are 10 centimeters, 15, 20, 25, and 30. Those are the lengths of those flags, colored flags that are on top of the cart. And what we're getting here, we're going to do 5 trials. We're getting the time it takes that 10 centimeter flag to pass through the photo gate. So the photo gate basically records the time it takes that 10 centimeter flag to pass through. If I launch it consistently, these values will be pretty much the same, right? I'm trying to launch it at the same speed. Then I increase the flag length to 15 centimeters. And again, I measure the time it takes. I'm doing 5 trials, time it takes that 15 centimeter flag to pass through the photo gate. And I do this for all 5 of these lengths. Okay, so then once you have all your data here, what you want to do is you want to first compute the average time that it took the flag to pass through the photo gate for each of these conditions, right? For each of these flag lengths. So basically, you're going to average these 5 values here, right? Make sure you use all 4 decimal places. So this should be rounded to 4 decimal places, right? So do that for each of these flag lengths, each of these conditions. Now, the last column here is delta x over delta t. That's your average velocity. So to calculate it, for instance, for the first case, you're going to take the change in position, which is really the flag length. The flag length really represents the change in position or the displacement. You're going to take that flag length, say 10, and divide by the average time it took to pass through, and that's going to be your average velocity. Then for the next one, you're going to take this flag length, 15, divided by the average time. That's going to be this velocity, and so on. Now, as a check to make sure that things are making sense, if you're being careful and you're launching the cart the same way every time, then what should be true about these values in this last column? Well, all these velocities should be basically the same, right? Now, they won't be exactly the same. It's very difficult to do the experiment exactly the same, but these should be very close to one another. In theory, they should all be equal. Okay, so hopefully they're at least very close to one another, these velocities. So basically what we're saying is as you increase the flag length, it takes longer to pass through the photo gate, but it's in proportion, right? Because I'm launching at the same speed. So the speed, when I calculate the speed, the velocity, it should be the same for all these conditions. Okay, so then in physics 212 and 207, you guys are responsible for questions 1 through 3. In physics 206 is basically just doing questions 1 and 2 in this part. So question 1 is plot position, which is delta, even though it's called delta x, this is really going to be on the y-axis, position versus time. So you might want to make note, this is going to be y, you're plotting this on the y-axis, these values, and then delta t is going to be on the x-axis. So if you do that, what do you get? Well, actually, let's go to the iPad to kind of look at this. Okay, so this is basically question 1, and I'm plotting position in centimeters on the y-axis versus time in seconds on the x-axis. And we know that since the velocity of the cart should be constant, this should be, the shape of this graph should be linear, right? This function should be linear. Now, it won't be exact, but let's say these are your points. So we definitely have 0, 0, right? And then let's say these are your points here. It might be off a little bit. But what you want to do is you want to do a linear fit to the data. And then when the computer does that fit, remember, it gives you the slope value. Well, what does that slope value represent? Well, we know what it represents, right? If we have position versus time, that slope should be equal to, and you're going to have the actual number, the actual value. It should represent the average velocity of the cart. And since it's linear, you could really make a stronger argument and say it should be the constant velocity of the cart, because we know the cart is moving at a constant velocity. So the slope, whatever value you get, should be the constant velocity of the cart. And of course, it'll be in centimeters per second with the units. Okay, so question 1 is do that graph on Pasco Capstone. Question 2, what is the shape of your graph? Don't forget to answer that in your laboratory report. What does the slope represent? And measure the slope. You don't have to measure it, you just have to record the value. So whatever value you get, you want to record that value in centimeters per second. Okay, question 3 is a second plot. Now you're going to plot average velocity versus time. So actually, let me go back to the handout for a second. Okay, so now question 3 is plot average velocity versus time, which means this last column, right, this is my average velocity, delta x over delta t, that's going to be on the y-axis. And then time, my average time will be on the x-axis. So time is the same, right? That's on the x-axis, but now my average velocity is on the y-axis. Now, this is the only one. In the first graph, you wanted to include the 0.00. That made sense. But in this graph, this is the only graph where you don't want to include the 0.00. You just want to plot these 5 values on the y and then these 5 times on the x-axis. Now, what should that look like? Again, let me go over to the iPad. Okay, so again, now I'm plotting average velocity, which is in centimeters per second. That's that last column, versus time in seconds. And just to note, remember, this is the one you don't want to include zero. Don't include the origin. Don't include 0, 0. It doesn't make sense to. Okay, well, we argued earlier that that last column, those average velocities, should pretty much be the same, right? Because I'm launching the cart the same way. It should be moving at a constant velocity. So the average velocity value should be pretty much the same. So, but the time we know is getting longer, right? Because it's the time interval is how long it takes the flag to pass through the photo gate. So as time goes on and I'm getting about the same average velocity, then my data is going to look something like this, right? These are about the same, right? So I'm making them off a little bit, but they're about the same. So in this case, what you want to do for the fit is you really want like an average fit. And the way that you do that, so it'll look something like this, let's say. The way that you do that is you press the sigma button. I'll note that here. Use the sigma button on Pascal capstone, and that will give you an average fit. The other thing you want to do is normally what it does, right, when it does a graph, it kind of zooms in and your values might be very close. Let's say your velocities are between like 70 centimeters a second and 80. So let's say these are your 5 values. If it zooms in, right, it doesn't look like it's linear because it kind of zooming in from 7 to 80. So what you need to do is you need to change the axis scale settings. So you need to change the y-axis scale settings. And you need to make like the minimum y value like maybe 0. And then it depends on what your actual values are. I would go a little bit above your highest velocity value. Like maybe in this case, let's say mine are between 70 and 80. I'd maybe go from 0 to like 85. And then it'll look flat, it'll look linear. Then you just do a sigma button and that gives you a nice average fit there, a nice average line. Okay, and then the rest of the question, so you do that plot for question 3. This is question 3. And then it says, what can you conclude from your graph? Well, if all these values are pretty much the same, if your velocity is horizontal, right? If it's a horizontal line, that's telling you what about velocity? It's telling you the velocity is constant. So it's kind of telling you the same thing that the first graph told you. Remember, the first graph was position versus time and it was linear. That also told you that the slope, which was the average velocity, is constant. So they're kind of telling you the same things. And actually, what you should find is that this average here, when you use the sigma button, it'll give you the average value here. This average should be similar to your slope from the first graph, right? Because they both represent the fact that the cart is moving at constant velocity. So let me write that here. So this average value should be similar to the slope value from the position versus time graph. because they're both representing the fact that the cart is moving at constant velocity. Okay, so that's it for the first part of the lab. And actually, again, physics 212 and 207 need to do all those questions. Physics 206 did not need to do question 3 here. All right, let's go to the second part. Let me go back to the handout and talk about the second part of the lab. Okay, so the second part of the lab deals with constant accelerated motion. So again, you have to watch my video lecture on how I collected the data. They're short videos, just me actually, putting the car in the air track and letting it run, letting it glide down the air track. So in this case, the air track was at an incline. I started the cart right before the flag triggered the photo gate, and I release it. And again, I'm getting the time it takes that flag, whether it's a 10 centimeter, 15 centimeter, 20, 25, and 30, the 5 different flag lengths, 5 different conditions here, the time it takes the flag to pass through the photo gate. So I'm collecting 5 trials for each of those flag lengths again. These are just the times. The second to last column, this is your average time. So you're simply gonna, once you have this data, and by the way, if you're watching this because you missed class, please get the data from your lab partners. Or if for some reason you can't, contact me and I will get you some data that you can use. Okay, so you're going to average those 5 values, right? And this last column, a second to last column, is simply the average time for each of those conditions. Again, make sure you round to all 4 decimal places. The last column here, it's called V2 in the lab manual. This is the VX final. This is your final velocity of the cart as the end of the flag passes through the photo gate. So this is that formula that we came up with earlier. So to calculate this last column, you have to find delta x divided by delta t, just like before, but then you multiply by 2. Remember, it's 2 times delta x divided by delta t, then 2 times 15 divided by this average time, then 2 times 20 divided by this average time, and so on. That'll give you the final velocity of the cart as the end of the flag passes the photo gate. What you should find, since the flag lengths are getting longer and longer and longer, that means the cart is accelerating for a longer time. You should find that these final velocities are increasing. So that's a good check, right? These values should be increasing over time. Okay, so the first question that you're responsible for is question 4. And what you have to do, it's a plot. You're going to plot position versus time. So delta x, which is your position, right, or displacement, that's going to be on the y-axis. And then delta t here is going to be on the x-axis. And you do want to include 0, 0 in this case. So what should that look like? Let's head over to the iPad to explain this. Okay, so again, I'm plotting position versus time, just like I did in the very first graph. But it's going to be different than the first graph. I remember the first graph was linear because we had constant velocity motion. In this case, we know that we have constant acceleration. In fact, we know that the velocity of the cart is increasing over time. Well, what represents the velocity? If I have a position versus time graph, we know it's the slope, right? The instantaneous velocity is the slope of the tangent line to that curve. If that slope is increasing over time, that means that this graph must be curving upward, right? Like a parabola. So when you plot your data, you might, your data might look like this. You have, 0, 0 is definitely a point. Let's say I have here, 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 here. You want to do a quadratic fit. So this should be a quadratic fit. And that should go through the data pretty well. So in Pascal Capstone, you can choose quadratic fit. Okay, and then don't forget to answer the questions from the lab manual associated with that. So do the graph. Then it says, how does this curve differ from that obtained in part A? We talked about that a little bit. And then there's sort of like a tricky question. It says, what is the slope of the curve? there's not really a slope, right? Because the slope is changing, but then you want to kind of explain that the slope, meaning the slope of a tangent line, it's changing, it's increasing over time. But that makes sense because we know in this case that the slope of the tangent line represents the instantaneous velocity, and we know the velocity of this cart is increasing over time. Okay, question 5 was simply to calculate. Let me go back to the handout for a second here. So question 5 was simply to calculate these final velocities, right? As the end of the flag passes through the photo gate. Remember, we should find that these are going to be increasing. One mistake students often make is they do delta x divided by delta t, but they don't multiply by 2, right? They forget to multiply by 2. Don't forget to multiply by 2. It's 2 times delta x divided by delta t. That gives you the final velocity, and these should be increasing. Okay, question 6 and 7, because 7 is just describing the graph. You're going to plot final velocity, which is your V2, right? Your Vx final, versus average time here. So V2 is going to be on the y-axis, and time again will be on the x-axis. All right, so let's talk a little bit about that. Okay, so now I'm plotting velocity versus time. I'll call it final velocity. Which is in centimeters per second versus time in seconds. Make sure you include 0, 0. So I'll plot 0, 0. Now, what should this graph look like? Well, again, we know that our cart, when it's on the inclined air track, is undergoing constant acceleration, right? So its velocity is certainly going to be increasing, but it's increasing at a constant rate because it's constant acceleration. So you should find the velocity is going up, but it should be linear, right? And it won't be exact. Let's say it looks like that. So you want to do a linear fit. Now, very important is the slope. What does the slope represent? Well, the slope here, the slope of this line, has got to be the acceleration, right? In fact, since it's linear, you can make a stronger argument. You can say this is the constant acceleration of the cart. And it'll have the correct units of centimeters per second squared. So it's the constant acceleration of the cart in centimeters per second squared. All right, and then question 7 just asks a couple of questions about this graph. Don't forget to answer them, like what is the shape of the graph? What does the slope represent? And then record that slope value. Right, when it says measure it, it means really record the slope value. So this is what we're calling, think of this as, we're calling this the experimental acceleration. That comes from the slope there is from that graph is the experimental acceleration. We're also going to calculate the acceleration theoretically, so we want to compare them. So remember that the slope from the graph is the experimental acceleration. Okay, and then the last question, and this is going to be for both physics 212 and 207, have to work on this. We want to calculate the theoretical acceleration. What is theoretically the acceleration of that cart? And it turns out to do this, I've done it here, but you need to really know Newton's second law. And I know some of you haven't studied that yet. So we're just going to kind of accept this formula as our theoretical value for the acceleration of the cart. So basically, it turns out that the acceleration in the x direction going down the air track here, it should equal g. Remember, g is that constant, the acceleration due to gravity. Because we're using centimeters, right, CGS units, g is, we're going to take it as 980 centimeters per second squared. If we were using SI units, like meters per second squared, then it'd be 9.8. But since it's centimeters second squared, and we know there's 100 centimeters in 1 meter, it's 980. Okay, so that's a constant. And in sine of theta, well, theta is the angle that the air track makes with the lab bench, right? It's that angle theta. However, it's very difficult to measure theta. So instead, what you're going to do, and I gave you a little table for this, you're going to measure the height of the air track at one end, say at the lower end here, I'll call this height 1. And then at the higher end, the one that's raised up, you're going to measure the height, again, just above the table of where that air track is. So that's height 2. So you're going to measure those in centimeters. And in using some basic trigonometry, we know that the length of this air track, it's a 2-meter air track, which is 200 centimeters. We can figure out that sine of theta is the same as the change in height, h2 minus h1, divided by 200. Okay, it's basically going to be opposite over hypotenuse, right? Sine of theta, SOHCAHTOA. Sine of theta is opposite over hypotenuse. The opposite is h2 minus h1, and the hypotenuse is the length, which is 200. So it's h2 minus h1 over 200. And that gives you sine of theta. So therefore, to calculate, once you have these heights, to calculate AX theory, your acceleration, theoretical acceleration, it's going to be 980 times h2 minus h1 over 200, right? Because I'm multiplying g times sine theta, but sine theta is h2 minus h1 over 200. So that'll give you AX theory. We already have AX experimental. That comes from the slope of that fourth graph, right? The final velocity versus time graph, that's from the slope. So now I want you to compare these two values by computing the usual percent experimental error. So think of the theoretical one as being the accepted gold standard one. So that's the one you want to divide by. Okay, and then that's it. So hopefully that made sense and you learned something about constant velocity and constant accelerated motion. Thanks.